Hey! In our last lesson, we discussed what standardization is. Let's see how it relates to our particular problem. When we calculated the coefficients of this regression without standardization, we could not immediately see the effect of each variable on the output. The reason is that SAT is ranging between 600 and 2400, while RAND 1, 2, 3 between 1, 2, and 3. Their respective coefficients were 0.0017 and minus 0.0083. So it seems like RAND 1, 2, 3 has a bigger coefficient, hence a greater impact. However, this conclusion could be wrong. Since the SAT score has a much greater magnitude, it is much more important. For instance, if Jane had 1800 on the SAT and the random number assigned to her was 2, then her expected GPA would be 1800 times 0.0017 plus 2 times minus 0.0083 plus the intercept. Obviously, the SAT expression is contributing a lot more to the final expression overall, as 1800 times 0.0017 equals 3.06, while 2 times minus 0.0083 equals 0.0166. However, by looking at the coefficients alone, one might be deceived. This issue is overcome through feature scaling. Having all inputs with the same magnitude allows us to compare their impact. Okay, now it is time to create new regression with the scaled inputs. Once more, let reg be equal to linear regression, and let's fit the scaled inputs and the targets. As usual, we will get nothing more than a line confirming that the regression had been successfully performed. To assess the actual difference, we can look at the coefficients and the intercept. Calling reg.coef and reg.intercept will help us with that. Before analyzing the results, I will arrange them in a summary table as before. This time, let's include the intercept as well. Let reg summary be equal to PD data frame, with data, intercept, SAT, and RAND 1, 2, 3, and with columns equal to features. Next, let's create a new series in that data frame called weights. Weights will include the intercept and the two coefficients, so reg, intercept, and reg, coef, 0 and 1. All right. Checking the contents of this summary, we see our three main ingredients: the intercept, SAT, and RAND 1, 2, 3 and their weights. You may be confused by the term weights. In fact, this is the machine learning word for coefficients. So far, we have not used it because, at least to me, it made little sense. Now, however, we have standardized the features, which resulted in standardized coefficients, or weights. The name comes from the fact that the bigger the weight, the bigger the impact of the feature on the regression. It carries weight on the result. In the same line of thought, in a machine learning context, the intercept is called bias. The idea is that the intercept is nothing but a number which adjusts our regression with some constant. But if we need to adjust our regression with some constant, then the regression is biased by that number. So ML practitioners simply call it bias. Okay then, let me change the word intercept to bias in the regression summary data frame. Great! We have achieved a regression summary which contains the features, the weights, and the bias of our regression. Using these new naming conventions, we can conveniently distinguish between a regular coefficient summary table and this new one with the standardized coefficients or weights. What about the interpretation of these weights? The closer a weight is to 0, the smaller its impact. The bigger the weight, the bigger its impact. In our example, the weight of SAT is 0.17, which is much bigger than that of RAND 1, 2, 3, standing at merely minus 0.007. This brings us to feature selection through standardization. We can clearly see that RAND 1, 2, 3 barely contributes to our output, if at all. It will make little difference if we remove it from the model or leave it there with a weight of almost 0, as 0 times any value is equal to 0. This concept is quite remarkable. When we perform feature scaling, we don't really care if a useless variable is there or not. This is also one of the main reasons why SKLEARN does not natively support p-values. Since most ML practitioners perform some kind of feature scaling before fitting a model, we don't really need to identify the worst performing features. They are automatically penalized by having a very small weight. In general, I always prefer to leave out the worst performing features as they interact with the useful ones and may bias the weights even if only slightly so. All right, let's wrap up here. In the next lecture, we will explore how to use this standardized model to make predictions. Thanks for watching.